Now we move on to rule number 3. Um, Rule number 3 is, what if you've got exponents that are applied repeatedly to a base. So let's say I've got a squared, okay, so I apply the squaring exponents, and then I hit that by an exponent that's 3, so that's a squared 2 to 3. So what is that equal to? Well, if I look at this carefully, this is a squared repeated 3 times, right? Multiplied 3 times by itself according to our definition. Now, how many copies of a are there? Well, there are 2 here, 2 here, and 2 here. Overall, there are 6 of them. 6 as in 2 times 3, right? So I can see that these 2 exponents that I have here, they can be multiplied in order to get my final answer, 6. Similarly, if I have a to the 3 squared, well, that would be a to the 3 times a to the 3 times a to the 3. So I would have, sorry, just twice, right? A to the 3 times a to the 3, so it's repeated twice. So I have what? 2 times 3 for my exponent. So same thing as before, since so this is equal here, and this is 6 again. Maybe to make things clearer here, instead of 2 times 3, I could have said this is 3 times 3 times 2, right? I've got 3 times the number 2 appearing, and here I've got 2 times the number 3. Just to show you that it's the same thing, because 3 times 2 and 2 times 3 are the same. So overall, it's 6 in both cases. So this gives us our next rule. If I've got a to the m to the n, that's also the same as a to the n to the m, right? So reversing the order of the exponent doesn't change the end result. And this is the same as multiplying the n and the m together, okay? So as an example, if I have 2 to the 3, 2 to the 2, then I'm allowed to multiply 3 and 2 together, so that's 2 to the 6. I'm also allowed to do this if one of them is a negative. So if I've got 2 to the 3 to the negative 2, I can still multiply them together. So 3 times minus 2, 2 to the minus 6, and that would be 1 over 2 to the 6. And maybe a little warning here. If I'm missing an n here, warning. If I have something like 2 to the 3 to the 2, if I see this, because there are no brackets, you see the I need to calculate this first. The exponent 2 applies to 3, so this is the same as 2 to the 3 to the 2, that's 9, right? So you see it's not at all the same. So if you write this, those are not equal, okay? Those are not equivalent expressions. So the brackets here play a major role. It forces you to evaluate 2 to the 3 first, okay? But ultimately, when you've got your brackets, you can multiply the 3 with the 2 together. When you don't have them, then you can't do that anymore. Rule number 4, if I've got AB, all that, raised to the power 3. So the rule I'm looking for is a rule when the base is a multiplication of two numbers. What does that give us? Well, this is AB multiplied 3 times by itself. Now if I look at the a's, they appear 3 times, so that's a cube, and same goes with the b, 3 times. So that shows you that we can sort of distribute this exponent over each factor that appears in the base. Same goes if I have a negative power. Why is that? Well, first of all, I can switch that to something with a positive power by sending AB square down. And then finally I can just say this is AB times AB. So this is A squared, B squared. That's the same thing as 1 over A squared times 1 over B squared. And that's the same thing as A to the minus 2 times B to the minus 2. All this showing again that you can sort of distribute the minus 2 over the A and the B, right? Which is what you get finally here, right? So overall, you could say that A to the M, even if M is a negative value, it's going to work. That's the same as A to the M times B to the M. You can distribute that M in some way over the factors that you find in the base. Maybe warning again, things that don't work. Because it's very tempting to, once you see a new rule, to apply something similar to apply this, try to apply this rule to a similar expression. But you'll see that things really don't work very well if you do that. So if instead of having A times B, I've got A plus B in the base, it's tempting to say, well, I'm going to distribute that M again, okay? Because I did that when they were multiplied, but it doesn't work here at all. So you can't, this is not the same as this, okay? This doesn't work at all, okay? So for example, if you've got A squared, A plus B squared, that's not at all A squared plus B squared. So you're not allowed to do this if things are added up in the base, okay? Maybe while we're here, I can show you other things that don't work. 1 over A times A plus B. Well, it's tempting to say, oh, 1 over A times B, that's the same as 1 over A times 1 over B. So if I put a plus there, maybe I can put a plus there. Well, actually, this is false. So this is not at all 1 over A plus 1 over B. So you can't do that. Do I have another? Yeah, well, same goes if you have this. You can't write, so this would be making, I don't know, 2 mistakes at once. So this is not at all like that. So you can't do that, okay? I guess that would come from if you've got a product here instead in the base. Yes, well, that's 1 over A to the M, B to the M. So that's really the same thing as 1 over M times 1 over B to the M. But if you put a plus sign in between the A and the B, it doesn't work anymore. So this is not equal. Rule number 5. If I've got A over B, all that raised to the 3. Well, what is this? Well, this is, according to our definition, it's A over B multiplied 3 times by itself. Above, I have 3 copies of A, below 3 copies of B. So I can see that even in this case, I can sort of distribute the 3. It also works if I have a negative power. Why is that? Well, it's because you can convert it first to a positive power by sending stuff down in the denominator. Then this is, according to our previous rule, A cubed over B cubed. And dividing by a fraction is the same as multiplying by its reciprocal. And you finally get this. Okay. Which I could also write as I could write this as 1 over A cubed times B cubed. And B cubed, I could also write that as 1, if I send the base down, I need to change the power of I need to change the power of the sign of the exponent. And 1 over a cubed, I can write that as a to the minus 3. So overall, that's a to the minus 3 over b to the minus 3. And I can finally regroup those together. So you can see that if I compare this to what I had initially, I can sort of also distribute the negative 3 to each part of the fraction. So this is the same as this, and also along the way I want to show you that it's the same as this as well. So I'm gonna sort of regroup that into my rule. So my rule, well, has sort of two parts. If I have a over b to the m, you can distribute the m independently of its sign. So you get this. But also what this example here shows us is that if I have a over b to a negative number, okay, by looking at this, you see you can sort of write it as b to the m over a to the n. So the m. So the m distributes, but at the same time, since there's a minus sign, it flips the numerator and the denominator. So this is also something to remember. So let's look at maybe two examples where we're going to apply all these rules now combined together. So I want to, so in the book you'll see the exercise written something like simplify, and you'll have an expression. So let's say you have this. So I've got a big expression. First of all, I recommend simplifying first your numerator and your denominator. Okay, so 3 times 10, that's 30. A cubed, right, this part times a to the 4, that's a to the 7. And I've got b times b cubed, so that's b to the 4. And below, there's nothing to do. Then you regroup like terms, okay, above and below, so these match perfectly. And also by writing the things in the variables in alphabetical order, they're already matched up. So 30 over 2 is 15, a to the 7 over a to the 4, that's a cubed, b to the 4 over b squared, that's b squared, and we're done. This is our final answer. Next example is slightly more complicated. So I've got one big fraction raised to the power 2. Over here I've got 3ab squared times, and there's a bracket here, 2a to the 4 b squared to the 3, and below 6a to the 5 b to the 7. So let's try simplifying this. So first let's handle the numerator and the denominator inside the larger brackets. So the first thing I'm going to take care of is this set of brackets. You see, everything is raised to the power, maybe I should use this, raised to the power 3. So I'm going to distribute that. I'm going to distribute 3 over each factor I find in the base. So I've got 3ab squared. I'm going to distribute that 3, so that's 2 to the 3. A to the... so what I have here is a to the 4, and I distribute the 3, so it's a to the 4 cubed. So that's a to the 4 times 3, so it's a to the 12. So here you multiply them, right? 3 times 4, 12. And same goes with the b squared when it's raised to the power 3. That's the same as b to the 2 times 3, so b to the 6. And all that is divided by 6, a to the 5, b to the 7. I'm going to simplify my numerator now. So this is 2 to the 3 is 8. Okay, this is 8. So 3 times 8, 24. A times a to the 12, that's a to the 13, b squared, b to the 6, that's b to the power 8, and below 6, a to the 5, b to the 7. Now let's try to simplify things by matching up like terms. 24 over 6, that's 4. 13, a to the 13 over a to the 5, that's a to the 8. And b to the 8 over b to the 7, that's just b. All that is squared, and now this is going to be distributed over each factor in the base. So 4 squared is 16. 8 to the 8 squared, that's 8 to the 8 times 2, 16. And b is finally squared, and that's my final answer.